6.1, Angles and Radian Measure. In Chapter 6, we're going to be moving away from the idea of degrees when we're talking about angles and thinking about them in terms of radians. And radian is a vocabulary term. Radian is a measure of an angle in standard position whose terminal side intercepts an arc length of r. And let me kind of show you what I'm talking about. So I'm going to draw an angle here. I'll draw it in green. So I got my initial side because we're in standard position, and my terminal side, I'm just going to say, looks like this. I'm just going to extend these just a touch, okay? And then my angle is here, theta, okay? The radius of my circle, I'm going to put a mark right here. The radius of my circle is r. Now, what makes this angle special and what kind of defines a radian is that the arc length, the part of the circle that is covered by this angle, that length there is also length r. So 1 radian, the length of the circle cut off by 1 radian, is the same distance as the radius of the circle. So what we can say here in this picture is that our angle here is equal to 1 radian. Notice radian and radius are spelled very similar. That's not a coincidence, okay? So our angle here, the radius and this arc length are the same, and that's what makes this angle 1 radian. If we wanted 2 radians, so we have our standard position angle going this way, and let's say we wanted to go somewhere out into here. Okay, there's that, and we have these points of intersection on the unit circle. This, let me do this in orange, this length here, covered by that, that angle. Let me draw this. I forgot to draw our angle theta. Theta here. Green from the center of the circle out to the dot is r. It's a length of r. It's our radius. We could assume it's 1, but we don't know that for sure. And the length of that orange line, the arc length of that circle that's covered by that angle is 2r. So if the arc length here is 2 times the radius, we could say that this angle in this second circle, the theta here, is 2 radians. Okay, so how do we formalize this, or how do we kind of think of radians in terms of numbers we're used to seeing? And that comes into circumference, and then 360 degrees, 180 degrees, and 90 degrees. If you remember from geometry, the formula for circumference of a circle is equal to 2 pi times the radius. Okay, well, you can think of this in terms of radians by thinking, okay, the circumference is 300, is all the way around the circle. So if our angle went all the way around, that would be 360 degrees. So then if our angle is 360 degrees in terms of radians, that would be 2 pi radians. 360 degrees is 2 pi radians. If we want to think about 180 degrees, that would be halfway around the circle. It would be half of our 360 degrees, so we just take this and cut it in half. Half of 2 is 1, so 180 degrees would be pi radians. And 90 degrees, whoops, let me fix that A, radians. And if we wanted to think about 90 degrees, and I'm going to do this in orange, if we want to think about 90 degrees, we would just cut our 180 in half. So pi cut in half is going to be, well, we'll just say it's pi over 2 radians. So those are very common measures in radians, from degrees to radians. We will be using pi a lot. Radians are generally written in terms of pi because 1 radian, if you think about just our picture here, if this is 1 radian, this is roughly like 57.3 degrees. But it's just easier to think of it in terms of pi and just whole numbers. So 2 pi radians, pi over 2 radians. All of the main or most common angles that we use on the unit circle are written in terms of pi, and we'll get to that here in just a second. The conversion formulas, if you're given something that isn't very familiar, like 180 degrees, maybe you're given 117 degrees, what would be the radian formula, or what would be the radian measure of that instead of degrees? To go from degrees to radians, what you're going to do is you're going to take your degree, the angle measure in degrees, times pi over 180. So whatever it is, let's say this was 117 times pi over 180. You could simplify 117 over 180. Well, if you can, do it. And then your pi is going to stay up top. To go from radians to degrees. So if I said convert pi radians to degrees, what you're going to do is you're going to take your radian measure, and you're going to take that times 180 divided by pi. Okay, so let's do a couple here. Convert the angle from degrees to radians or radians to degrees. So number one, we got a 115 degrees. The question might come up, how do you know if it's degrees or if it's radians? Usually degrees are written with this little symbol right here, the degree thing after the number. If it doesn't have the degree, like this one right here, 2 pi over 3 or negative 7 pi over 8, that's a pretty good indicator that it is radians. Also, if you see pi, like you do in these two examples, probably going to be radians. If it's going to be degrees, it will have the degree symbol after it. But since these don't or didn't originally, we can assume that those last two are going to be radians and we need to convert them to degrees. But let's do the first two, to convert degrees to radians. So to go from degree to radian, I've got it here in red, we're going to take our degree times pi over 180. So 115 times pi over 180 becomes 115 pi over 180. That's 115 pi over 180. 115 over 180. You can simplify that down. You can use your calculators to simplify them. If you're not sure, just let me know and I will show you how to do that. 115 over 180 does simplify down into 23 over 36, and that's 23 pi over 36. That would be the radian measure for 115 degrees, 23 pi over 36. 200 degrees works very, very similarly. We're going to take 200 times, and I'm just going to do it here with the one I already wrote, pi over 180, which becomes 200 pi over 180. 200 over 180 does simplify down nicely. We can drop those zeros on the end of it, so it becomes 20 over 18, which is something a little more easier to do in your head. 20 over 18 does simplify down into 10 over 9, so it's going to be 10 pi over 9. So there's your two degrees to radians. Now let's do radians to degrees. To go radians to degrees, we have it at the top of the screen here. We take our radian measure times 180 over pi. So I'm just going to take 2 pi over 3 times 180 over pi. Now something really nice happens. We got a pi on top, we got a pi on bottom. Those cancel each other out. You could simplify 180 over 3. That's a 1. 180 divided by 3 is 60. So then we're left with just 2 times 60, which is 120 degrees. Pardon my bunching here of my writing. I'm at the bottom of my slide and I can't go any farther. So number 3 is 120 degrees. Number 4, negative 7 pi over 8. Once again, we're going from radians to degrees, so we're going to take our radian measure times 180 over pi. Again, the pi's cancel out. If you just want to do 7 times 180 divided by 8, feel free. What you're going to get when you do that is negative 157.5 degrees. So if it's asking for a degree measure, you can actually do decimals. Usually with radians, we probably want to leave things as fractions. Earlier in chapter 5, we looked at the unit circle and we filled in the unit circle with sines and cosines and angle measures, but we left the angle measures in degrees. Let's do that. Let's fill in our unit circle, because on that unit circle sheet I gave you, you should have one more space, and we're going to fill in the radian measures for each of these angles. Okay, we already know some of these angles. We know 0 is also 360. So then 0 and 360, 0 degrees is just going to be 0 radians. 360 degrees, we saw this earlier. I'm going to go way back up at the top. 360 is 2 pi radians. So 0 slash 2 pi is going to go on that line next to 0 and 360. 180 degrees, we know what that was. That was pi radians. 90 degrees is in between 0 and pi, which was pi over 2. Pi over 2. I'm actually going to make that a vertical fraction, pi over 2. I'm going to need all the space I can get. 270 degrees. So if you look, if we go every 90 degrees, we're adding 1/2 of a pi. So we got 0 pi, half a pi, a whole pi. Next would be 1 1/2. And we don't usually write mixed numbers. We usually write them as improper fractions. 1 1/2 in terms of, or as an improper fraction, is going to be 3 pi over 2. Okay? So there's your x and y coordinate plane, your x and y axis in terms of radians, 0, 2 pi, pi over 2, pi, and 3 pi over 2. Now we have all these other angles, the 0, the 30, 45, 60, and then everything else around the circle. If we think about it, if we look at the 45 degree marks, so that'd be 45, 135, 225, and 315. So basically 45 is halfway in between 0 and 90. So half a pi, so if I have a pizza and I cut it in half, and then I cut it in half again, so if I'm just looking at this is my 1/2, and now I split this half in half, that leaves me with 1/4. So 45 degrees is going to be pi over 4. I'm going to use different colors when I get to 60 and to 30 and 60 degrees, just so it's easier to follow on this video. So if we go 45 degrees is 1/4 of a pi, so 1/4, another 1/4 gets us to a half. One more 1/4 gets us to 3/4 pi, or 3 pi over 4. One more fourth would be 4 pi over 4, which 4 over 4 simplifies to 1. One more fourth, so 4 pi over 4 plus 1 pi over 4 gives me 5 pi over 4 at 225. 6 pi over 4 simplifies down into 3 pi over 2, and then one more pi over 4 gets me to 7 pi over 4, that's at 315, and then 8 pi over 4, that simplifies down into 2 pi. Okay, so we've got our 45 degree marks along with our 90, 80, 270, and 360. Now we need to think about the 30 and 60 degree marks. I'll do the 30 degree marks first. So 30 degrees would be basically a third of 90 degrees, correct? So when we take 1/2 and we cut it in thirds, a third of a half is 1/6. So this will be pi over 6. Okay? So if we go another 30 degrees, that's another pi over 6. So 1/6 plus 1/6 is 2/6. 2/6 simplifies down into 1/3. So this is going to be pi over 3. Okay, so 30 degrees is pi over 6. 60 degrees is 2 pi over 6, or pi over 3. And we'll just keep going. So if we just keep adding pi over 6 every time, we'll be able to fill in the rest of the unit circle. So we have pi over 6 here, 2 pi over 6, 3 pi over 6, another 30 degrees would be another pi over 6. So this was 3 over 6, which makes this 4 over 6, and 4 over 6 does simplify into 2/3. So this will be 2 pi over 3 at 120 degrees. 5 pi over 6 would be next, and 5 over 6 doesn't simplify, so 150 is 5 pi. Oh, that's a really bad pi. Let me try that again. 5 pi over 6. If we go another pi over 6, that's 180 degrees. That's 6 pi over 6, which is 1 pi. Another 30 degrees would be 7 pi over 6. 7 pi over 6. Another 30 degrees would be 8 pi over 6. 8 over 6 does simplify down into 4 over 3. So 4 pi over 3 at, ooh, that's really bad. At, let me erase this. Let me try again. 4 pi over 3. The next 30 degrees would be, let's see, 7, 8, 9 pi over 6. 9 over 6 simplifies into 3 over 2. And then we have 10 pi over 6. 10 over 6, let's see, they're both divisible by 2, so that'd be 5 over 3. So 5 pi over 3 at 300 degrees. And then one more sixth, so that'd be 10 over 6, so that'd be 11 pi over 6 at 330. 11 pi over 6. And if we go one more, 12 pi over 6, 12 over 6, that's 2. So there's your filled in unit circle in terms of radians. We are going to be using radians a lot in chapter 6 and in the future when we're talking about trigonometry. So you need to be familiar, or need to get yourself familiar with these angle measures. If you want to think of them in terms of degrees and convert them to radians, that's fine. But the sooner you can be more familiar with where these angles are on the unit circle, the better off you're going to be. So let's do a little bit of practice here. Evaluate. Cosine of 4 pi over 3. So 4 pi over 3 is down here. It's 240 degrees. So the sine and cosine are going to be exactly the same, whether it's degrees or radians. So if you look at your unit circle and you find 240 degrees, or you find 4 pi over 3, the cosine of 4 pi over 3 is going to be, if you look at 240 or 4 pi over 3, that's going to be negative 1/2. And that's as simple as it gets. Let's try another one. Number 2. Let's go with the sine of 3 pi over 4. Once again, 3 pi over 4 is on your unit circle. 3 pi over 4. So there's 1 pi. 3 pi over 4 is there. 135 degrees. Let's see. We're looking for the sine of 3 pi over 4. If you find 3 pi over 4 on your unit circle, sine of 3 pi over 4 is going to be negative, not negative, it's quadrant 2, and sine in quadrant 2 is positive. It's going to be positive square root of 2 over 2. The sine and cosine at the pi over 4 numbers, let me go back here. The sine and cosine at your pi over 4, whether it's 45, 135, 225, 315, the numbers are exactly the same. It's always square root of 2 over 2. It's just a matter of determining what signs are what. Now, what if they were angles that weren't on the unit circle, like the tangent of 25 pi over 6. 25 pi over 6 is not on the unit circle. We need to find its reference angle. We need to find something that is between 0 and 2 pi, and since we're talking 6, we need our numerator to be between 0 and 12, because 12 pi over 6 is 2 pi, which would be one full time around the circle. Okay, so 25 over 6. What I'm just going to do, I'm going to start subtracting 12 pi over 6, because that's one time around. 12 pi over 6 is 2 pi. So then that's just eliminating one extra revolution. So 25 minus 12, that's, that's 13 pi over 6. But that's still too big. That's still one full rotation plus a little more. So I'm going to subtract another 12 pi over 6, and that's going to give me pi over 6. That's something that's on the unit circle. Pi over 6, 30 degrees. We know the tangent of 30 degrees. It's back in chapter 5 if you've kind of memorized it or gotten yourself a little more familiar with it. That would be nice. It would be tangent. We can say the tangent of 25 pi over 6 is the same thing as the tangent of pi over 6, which tangent of pi over 6, same thing as tangent of 30. That is the square root of 3 over 3. Let's try one more here. Number 4. Let's find the sine of 11 pi over 3. Okay, once again, since we're talking in thirds, this number needs to be twice as big as the bottom to be one revolution. So 6 over 3, 6 pi over 3 is what we're looking for, something less than 6 pi over 3. So let's just start subtracting 6 pi over 3, and that'll give me, let's see, 5 pi over 3. And 5 pi over 3, that's on the unit circle. That's right here at 300 degrees. Okay, so we're looking for the sine, so we're looking for 5 pi over 3, so we could say the sine of 11 pi over 3 is equal to the sine of 5 pi over 3. And when you look at your unit circle, sine of 5 pi over 3, that is, let's see, that's negative square root of 3 over 2. The last couple of items in section 6.1 deal with some applications of radian angle measures. And we start with circles. Okay, so we got two vocabulary terms here, circular arc and central angle. Central angle I'm pretty sure you've heard of before in geometry. Circular arc, possibly. I don't know off the top of my head. But circular arc is a part of a circle, just so like something like that I've got highlighted in orange. That's a circular arc. A central angle is an angle whose vertex lies at the center of a circle. So if I were to draw the center of a circle right there, and I were to draw an angle that went through the circle, this right here would be my theta. This is my central angle that I've drawn there in green. And the arc length of the circular arc is in between the angle. Okay? So the question becomes, and what we talk about first in this section in terms of application, is finding this length right here, this arc length. This, what I've got highlighted there in orange. And here's how you find it. The arc length is equal to the radius of your circle, and you'll be given that, times the angle in between. Now, it's important that we know if the angle goes counterclockwise, if it goes clockwise, or if it goes counterclockwise from the outside to the inside. Okay? The angle, when you're doing arc length, has to be in radians. Okay? If it's not in radians, you're not going to get the right answer. Okay? So the radius, that'll be given. The angle will also be given. You might not be given an angle in radians. You'll need to convert the angle to radians if it isn't given to you in radians. So let's try a couple of examples here. Find the arc length with a given radius and central angle. So number 1 here. Your angle is going to be 125 degrees. So right away we're going to have to convert that. And our radius is 7 centimeters. Okay? So first thing we need to do is convert 125 degrees to radians. How we're going to do that, if you remember, 125, your angle measure in degrees, times pi over 180. So 125 times pi over 180 is going to be 125 pi over 180, and we'll have to simplify 125 over 180. They're both divisible by 5, and that's the only thing they're both divisible by. So that's going to give us 25 pi over 36. That is your angle measure in radians, and you need to make it in radians in order to find arc length. Once we've got our arc length or our angle figured out in radians, we can go ahead and put it into the formula. The arc length, by the way, and I never gave this to you, the symbols for arc length, the book uses lowercase s. I really don't know why, but that's the letter they use, so that's the letter I'm going to use. So the s is equal to the radius times your angle. And again, the angle needs to be in radians. So our arc length here, s, is equal to our radius, which is 7, times our angle, which is 25 pi over 36. You can type this directly into your calculator, as written. 7 parenthesis 25 pi slash 36, close the parenthesis, and you're done. And when you do that, you find that the arc length here is approximately 15.3 centimeters. Let's try another one here, number 2. Our angle is 2 pi over 3. So this is already in radians. We're not going to need to do any converting. And our radius here is 1.4. It doesn't give us a unit, so we'll just say 1.4. Okay, so we'll leave that vocabulary term there just a second. So we don't need to convert, so we can go right into the formula. S equals, arc length equals our radius of 1.4 times our angle, 2 pi over 3. And again, you can type this directly into your calculator, round to the nearest tenth. It doesn't really say to, but I'm going to. We're going to find that the arc length is 2.9. And since we don't have a label already, we'll just say units. So the question might be, when do you use this? There's an example in Algebra 2 of finding the length of a fence of a baseball or softball field. If the field was circular, or if the fence was circular, that would be an example of you finding arc length. Something like that would be definitely an example. The last part of this section is the idea of a sector. Okay, and sector is a vocabulary term. It's a region of a circle bounded by a central angle in the intercepted arc. So get that written down, and I'm going to scroll back up because the sector in my picture here would be this area. We're going to assume that it's the angle, that the angle goes from the horizontal part to the other angle, or the other extended side. Okay, so the blue area here would be the sector of this circle. The formula for area of a sector is equal to 1/2 times the radius squared times the angle. And you really don't need these parentheses, so I'll get rid of them and rewrite this here. 1/2 r squared theta. And once again, your angle needs to be in radians, and you might want to write that off to the side. In radians. Your angle has to be in radians. If it's not in radians, it's not going to work. So we need to make sure that our angle is written in radians. Got one example here for you for the area of a sector, and then that'll be the end of the video. So in the universe, the most common elements are hydrogen at 73.9%, helium at 24.1%, oxygen at 1.07%, and all the others combined at 1.03%. On a circle graph with a radius of 1 inch, what area of the circle should represent hydrogen? So if I were to draw a picture, so here's my circle graph, my radius is 1, 73.9%. So if I'm just thinking, that would be 25, that's 50, there's 75. So not quite this, not quite 270 degrees. So this would be my angle. Here's theta. And then I'm just going to outline it. This area right here would be my sector. So what area of the circle should represent hydrogen? Here's how I would solve this. First thing I need to do is I need to figure out what my angle is. And I need to find 73.9% of my circle. And in a circle, you have 360 degrees. Okay? So 73.9% of 360, we're going to take 360 times 0.739. And when we do that, we're going to get roughly 266 degrees. Okay, so there's our angle measure in degrees. We need to convert that to radians. So I'm going to say 266 times pi over 180. And when we do that, we're going to get, after we simplify it, we're going to get 133 pi over 9. Scratch that, 90. 133 pi over 90. So there's our angle. This is theta. Now we know our radius of 1. going back to our formula, we have enough to figure out the area of that sector. So area equals, we're going to take 1/2 times my radius, which was 1 squared, times my angle, which was 133 pi over 90, and type that into your calculator. 1 squared basically goes away, so really it's 1/2 times 133 pi over 90, and when you type that into your calculator, what you're going to find is the area of that circle graph is approximately 2.3, and let's see, do we have a label? We do. We have inches, and since we're talking area, it is square inches.